Welcome to this lesson on Descartes' solution of the quartic equation. Imagine trying to break a giant, complex boulder into manageable pieces. You wouldn't smash the whole thing at once. Instead, you'd chip off the awkward edges, find a natural fault line, and split it into smaller rocks. Today, we will learn a brilliant algebraic method developed by René Descartes in 1637 that does exactly this to fourth-degree polynomials. Now that we know our goal, let us look at the strategy. Why does this concept matter? Because solving a degree 4 polynomial directly is incredibly messy. Descartes realized that if we can just remove the third degree term, the equation becomes much cleaner. We call this a depressed quartic. Once we have this cleaner equation, we make a clever assumption that it can be split into two second-degree equations. Since we already know how to solve quadratics, this turns an impossible problem into a sequence of easy steps. To begin this process, we start with the general form of a quartic equation. Here, a, b, c, d, and e are known constants, and x is our unknown variable. If any of these variables change, the shape of the graph shifts. To eliminate the x cubed term, we substitute a new variable, y, using the relation x equals y minus b over 4a. Conceptually, this shifts the entire graph left or right until the cubic part disappears. When we expand this, the cubic terms perfectly cancel out. This leaves us with the depressed quartic, which only has terms for y to the fourth, y squared, y, and a constant. The letters q, r, and s represent our new calculated coefficients. With our depressed quartic in hand, we move to Descartes' brilliant assumption. He proposed that this fourth-degree polynomial can always be factored into the product of two second-degree polynomials. Notice a deliberate choice here. One quadratic will have a positive k times y term, and the other a negative k times y term. Why? Because when we multiply these brackets together, those terms will cancel out, perfectly matching our depressed quartic, which has no y cube term. Our goal now is to find these unknown numbers. To find those missing numbers for our quadratics, we use a special third-degree equation called the resolvent cubic. Conceptually, this formula is built by matching the coefficients of our assumed quadratics to the depressed quartic. In this formula, the symbol t represents the square of our unknown value k. The symbols q, r, and s are simply the numbers from our depressed quartic. If the value of s increases, the constant term in our cubic changes, shifting its roots. By solving this cubic equation for t, we can find k, which then unlocks the rest of the problem. Before we look at how the resolvent cubic is derived, let us see it in action. We are asked to find the roots of x to the fourth minus 2x squared plus 8x minus 3 equals 0. Notice there is no x cube term, so it is already depressed. We identify our coefficients. Q is negative 2, r is 8, and s is negative 3. We plug these values directly into our resolvent cubic formula. Simplifying the arithmetic carefully gives us a clean third-degree equation in terms of t. Continuing with our equation, we need to find at least one valid root for t. We can solve this by factoring by grouping. We group the first two terms and the last two terms, factoring out the common elements. This reveals a common binomial factor of t minus 4. Setting the brackets to 0, the first bracket gives imaginary numbers, but the second bracket gives us exactly what we need, t equals 4. Since t is k squared, we take the positive square root to find that k equals 2. Now that we have k, we must find L and M. We use two simple linear equations that come from the method's derivation. Plugging in our known values, we find that the sum of M and L is 2 and their difference is 4. Adding these equations together cancels out L, giving us M equals 3. Substituting back, we find L equals negative 1. We now have our two quadratics. Using the standard quadratic formula on each bracket gives us our final 4 roots, 2 real and 2 complex. Let us tackle a harder problem, where the equation is not already depressed. We have a full quartic with an x cubed term. To remove it, we use our substitution formula, which tells us to replace x with y plus 1. We substitute y plus 1 into every instance of x in the original equation. Expanding these brackets requires patience, but after grouping like terms, the cubic terms perfectly cancel out, leaving us with a new depressed quartic in terms of y. From our new depressed quartic, we identify our coefficients. Q is -8, R is 9, and S is -2. We plug these into the resolvent cubic formula. Simplifying the arithmetic gives us a specific cubic equation for t. By testing small integer values, we find that t equals 9 is a valid root, because plugging in 9 makes the equation equal exactly 0. This gives us the key to unlock the rest of the problem. Since t is 9, our k value is the square root of 9, which is 3. Next, we find L and M using our sum and difference equations. The sum of M and L is 1 and their difference is 3. Adding the equations gives 2M equals 4, so M is 2. Substituting back gives L equals -1. We can now write our original quartic as the product of two quadratics in terms of y. We solve these two quadratics. The second one factors easily, giving y equals 1 and y equals 2. The first requires the quadratic formula. But remember, these are values for y. Our original equation was in terms of x, and our substitution was x equals y plus 1. We must add 1 to all our y values to get the final answers. We have successfully broken the large problem down and found the 4 exact roots. Now that we have successfully used the resolvent cubic, let us understand where it comes from. This chunk of the proof establishes the foundational equations. We start by expanding our assumed product of two quadratics. This expanded form must be exactly identical to our depressed quartic. Because they are identical, the coefficients of matching terms must be equal. The mathematical reasoning here is simple polynomial equality. The number in front of y squared must equal q, the number in front of y must equal r, and the constant term at the end must equal s. This gives us a system of 3 equations, which we will manipulate in the next step. Moving forward with our derivation, we rearrange our first 2 equations to isolate the sum and difference of m and l. Now we connect these using a famous algebraic identity. The square of a sum minus the square of a difference equals 4 times the product. The intuition here is to eliminate m and l entirely, leaving an equation with only k and our knowns. We substitute our expressions for the sum, difference, and product into this identity. This equation now only contains our known numbers, q, r, s, and the single unknown k. To clear the fraction and make it easier to solve, we multiply every term by k squared. This brings us to the final stage of our derivation. This equation looks complicated because it would have a k to the 6th power if expanded. However, notice that k only appears as k squared or powers of k squared. To make this easier, we introduce a temporary variable, t, defined as k squared. Substituting t transforms the equation into something much more manageable. Finally, we expand the squared binomial and multiply everything out. Grouping the terms gives us our final result, the standard third-degree polynomial equation known as the resolvent cubic. We have successfully proven the formula we used earlier. Let us visualize the entire journey we just took. We start at the top with the original quartic equation. Our first major step is shifting it to remove the cubic term, creating the depressed quartic. From there, we construct the resolvent cubic and find its root t. This crucial value allows us to split the problem into two separate quadratic equations. Finally, solving those two familiar quadratics yield the four final roots. It is a beautiful, logical flow from complexity to simplicity. Why does this complex method matter in the real world? Quartic equations appear frequently in physics and engineering. For example, calculating the exact intersection points of two conic sections, like planetary orbits, or rendering curved surfaces in video games, often results in a quartic equation. In optics, tracing light rays through complex lenses involves fourth-degree polynomials. Descartes' method proves we can find exact analytical solutions without relying on computer approximations, which is crucial for high-precision engineering. To summarize, Descartes' solution is a brilliant algebraic trick to break down a degree 4 polynomial. We first remove the cubic term to create a depressed quartic. By assuming the result is the product of two quadratics, we create a system of equations solved using a third-degree resolvent cubic. This ultimately gives us the coefficients for our quadratics, turning an impossible-looking problem into a sequence of manageable steps. You now have the tools to solve any quartic equation.